Hello and welcome to Vodcast 2.5. This is the final Vodcast for Chapter 2, and it's the final puzzle piece for my presentation of the rock cycle. Let's go over some of the key characteristics of metamorphic rock. Alright, we've come full circle in understanding this picture. We talked about how magma and lava will form igneous rock, and igneous rock can be weathered, transported, and then deposited to form layers of sediment. As those sediment layers pile up, there's extreme pressure exerted on the sediment layers below, and once lithification occurs, you form sedimentary rock. Well, now we're going to talk about metamorphic rock. And metamorphic rock is produced from pre-existing igneous rock, sedimentary rock, or even other metamorphic rock. Not to get ahead of ourselves, but if metamorphic rock melts deep beneath Earth's surface, it forms magma, and the cycle starts anew. As stated just a moment ago, metamorphic rocks are produced when pre-existing parent rock is transformed. On the screen right now is a picture of my daughter and I. And just as I am the parent to my daughter, every metamorphic rock that exists has a parent rock. Let's break away from the father-child analogy and talk about what metamorphism is. When you hear the term metamorphism, you should think about change. And it occurs when the parent rock is subjected to a different physical or chemical environment. The parent rock could be subjected to either elevated temperatures or elevated pressures. Metamorphism can change the mineralogy, the texture, and even the chemical composition of the rock. And it's also important to note that metamorphism progresses incrementally. There's low-grade and there's high-grade metamorphism. Let's look at the example for slate, which is a very popular building stone. The parent rock for slate is shale, which is a sedimentary rock. And shale has very loosely packed clay minerals. It's a fine-grained sedimentary rock. Now, shale will undergo low-grade metamorphism at relatively low temperatures and pressures. And when it does so, you see that there's new alignment for the chlorite and mica minerals. So what are the agents for metamorphism? Put as simply as possible, we could actually make this list 3 instead of 4. And the 3 primary agents are heat, pressure, and chemically active fluids. We're going to be a little bit more specific when it comes to that term pressure. And we're going to expand that agent to include both confining pressure and differential stress. The first agent we're going to consider is heat, which is a form of energy, and the heat energy originates from either the intrusion of magma or the burial of rock. This is considered contact metamorphism because if you imagine a hot stove and then putting your hand on it, you know that heat energy is going to be transferred from the hot stove to your hand and you're going to get burnt. Well, the same thing happens to the parent rock that gets subjected to heat. Instead of it getting a blister from the heat, it will undergo metamorphism and form a metamorphic rock. The top image shown shows confining pressure, and the red arrows shown indicate the magnitude of the pressure, which is proportional to force in the area in which the force acts. We see that the pressure is equal in all directions because of burial. If you look at the cube of undeformed strata and then the cube of deformed strata, you can almost think of it as confining pressure is just going to squeeze that undeformed cube into a much, much tighter, more densely packed cube. Differential stress is a little bit different than confining pressure, because with confining pressure, we saw pressures equal in all directions. With differential stress, the pressure will be greater in one direction than the other. We often see confining pressure in regions of mountain building, as shown in this image. And mountain building is an excellent example of what we call regional metamorphism. So in the image shown, we see that the pressure acting in the horizontal direction is far greater in magnitude than the pressure acting in the vertical direction. The vertical arrows are very small, pressing inward, but the horizontal arrows are quite big, pressing inward. So if we started off with our nice little pretty cube, differential stress isn't going to squish it into a smaller cube. It's going to reshape it into a more oblong rectangular solid, as shown in this picture. Differential stress often produces those really cool zigzag bands that look kind of like Charlie Brown's shirt. And under differential stress, the rocks can either break or bend, depending on the temperature. The last agent of metamorphism that we'll consider is chemically active fluids. In really hot regions, these ion-rich fluids can surround minerals and act as catalysts that promote recrystallization. Chemically active fluids can change the chemical composition of surrounding rock. Metamorphic rocks can be classified based on their texture, and the 2 texture descriptions are foliated and non-foliated. Foliated refers to the flat, banded appearance of the mineral grains. For example, if you look at slate, you see that the grains all run parallel to one another, in a pretty flat alignment. On the flip side of the foliation coin, let's consider the non-foliated metamorphic rock textures. You won't see a flat, banded appearance in these particular rocks, and marble is a great example of a non-foliated metamorphic rock. The parent rock for marble is often limestone, and limestone can be metamorphosized by the intrusion of a really hot magma body. That magma body will provide thermal energy, or heat, and it will do so by way of contact metamorphism. And when that occurs, limestone will form the metamorphic rock, marble. Okay, that concludes the final video podcast for Chapter 2. I hope these videos have helped solidify your knowledge of the rock cycle, pun intended. And at this point, we're going to transition from talking about rocks, minerals, and solid earth to landscapes fashioned by water. In our next series of video podcasts, we're going to be focused on where the rock cycle meets the water cycle, and that dynamic interface occurs at Earth's surface.